In this video, we will discuss how PCA is used to reduce the dimensions of a dataset and how much information is lost with this reduction. Principal component analysis of a dataset is finding the principal component directions and the variances along each component. Those are found using the eigenvalue decomposition of the covariance matrix of the data. We can summarize the steps for the PCA in the following graph. PCA starts by pre-processing the data points. This pre-processing step centers the data points around the origin so that the mean of the data features is always 0. These will be our data points from now on. The next step in the PCA is to compute the covariance matrix of the pre-processed data. That will be the input to the eigenvalue decomposition step. The PCA applies eigenvalue decomposition on the data covariance matrix to get the eigenpairs of the covariance matrix, which are the principal components of the data. The eigenpairs are then ordered so that the eigenvalues are in descending order. Now, U1 is the direction that contains the maximum variance, lambda 1, of the data. U2 will contain the second most variance, lambda 2, in the data, and so on. Those direction vectors are then concatenated in one n by n matrix. This is the PCA projection matrix, where each column is a principal component direction. The first column will be the direction of the maximum spread. The second column will be the direction of the second largest variance or the second largest spread in the data, and so on, till the direction of the minimum variance of the data, which will be on the UN column vector. Remember that all the principal component directions are orthogonal to each other. It acts like a rotated version of the original dimensions or feature space. This matrix is used to project the zero mean data points on the principal component directions. Projecting the zero mean data points using the projection matrix will move each point from the XY feature space to the principal component feature space. We would now like to use the PCA to reduce the dimension of the data. In our example here, we need to go from 2 dimensions to only 1 dimension, so from 2 features to 1 feature. To do so, PCA will project the data points only on the major principal direction. That way, every point of 2 features in the original space will get mapped to 1 dimension in the PCA space. What we gain using PCA to reduce the dimensions is that it projected the data on the direction of the maximum variance instead of any other direction in the data. This can be generalized to any n dimensions feature space, of course, to move from n features or n dimensions to k dimensions. The data is projected on the first k principal component directions, the ones that have the maximum amount of variance. That will ensure that in the k-dimensional space, we lose minimum amount of variance in the data. A nice property of PCA technique is that it preserves the variance of the data. This means that if we sum all the variances along the original dimensions, it will be the exact sum of the eigenvalues, the lambdas, or the variances of all the principal components of the data. Going back to our example, the sum of variances of the x dimension and the y dimension is equal to the sum of lambdas, lambda 1 plus lambda 2. We can measure the exact amount of variance kept when dropping some dimensions. This can be done by simply adding the lambdas that correspond to the KPC directions that we keep. We can also calculate the percentage of the variance kept after the dimensionality reduction using the percentage equation on the slide. We choose K based on the application, but most commonly we aim to keep around 90% of the data variance. In this video, we went through the steps of PCA technique, we explained how PCA performs dimensionality reduction, and we were able to calculate the exact amount of variance kept in the data after applying the PCA reduction technique. I hope by now you have a better overview of how PCA works and will be able to apply it in real-life machine learning problems.